Hello, my name is Dr. William Benzing. My background is in geophysical sciences. I would like to present to you the smoking gun hydrogen prospect. There are two purposes for drilling this prospect. First of all, I want to drill an economically viable white hydrogen well. Secondly, I want to verify three novel exploration concepts that can be used to locate additional significant, producible, and sustainable hydrogen reserves in buried mountains. Before talking about the three exploration concepts that were used to find the prospect, I want to show you a geologic cross-section through the Smoking Gun prospect. The prospect is located in the buried Wichita Mountains of southwest Oklahoma. The hydrogen reservoir, shown in blue, is located within a basement-involved, almost flat-lying, recumbent fold. The upper limb of the fold has been almost completely eroded by the Wichita unconformity, leaving the lower limb of the fold primarily cored in Arbuckle dolomite in pink, along with sandstone, shale, and granite wash. The reservoir rock is the iron-rich dolomite, which is sealed by a thin granite as a result of the unconformity. A shallow, abandoned natural gas field of Permian age sits above the calculated 64 BCF hydrogen reservoir. The prospect can be tested by drilling a 5,500-foot exploratory well. Now that you have been introduced to the Smoking Gun hydrogen prospect, I would like to talk about the first of the three exploration concepts that were used to build the prospect. As shown in this slide, the concept originated based on data from an off-structure wildcat well. The concept states, the presence of dispersed and mobile nanomagnetite crystals in the swabbed pore fluid of a porous, iron-rich dolomite is an indicator that subsurface hydrogen has migrated updip within the dolomite. The nanomagnetite is the smoking gun when it comes to hydrogen generation and migration. Let me explain. I entitled this slide Years in the Making. It explains the first novel exploration concept for locating geologic hydrogen. In 2004, I participated in the drilling of the down dip and off-structure wildcat well that you saw on the previous slide. The intent was to produce oil or gas. A porous zone in the iron-rich Arbuckle dolomite was tested by swabbing formation fluid. The swabbing produced black salt water but no commercial hydrocarbons, only a weak gas flare was observed after shutting the well in. Given time, the water cleared up, leaving a layer of black sediment in the bottom of the drill pit. The black layer was determined to be magnetite, the only magnetic mineral in the Earth. Further analysis determined the magnetite crystals to be nanosized. The presence of dispersed nanomagnetite crystals moving through the porosity of a dolomite rock puzzled me for many years. 20 years later, thanks to the recent interest in hydrogen exploration, I have a scientific explanation for the nanomagnetite. Let me explain. The search for naturally occurring hydrogen in the Earth involves the geochemical process of serpentinization. Serpentinization converts ferrous iron containing minerals and water to magnetite plus hydrogen gas. This video shows the formation of black magnetite and hydrogen gas associated with serpentinization. The magnetite was considered a catalyst in the formation of hydrogen, but recent studies suggest that magnetite is the primary source of the hydrogen. Let me explain how the role of magnetite has changed. Within the last decade, scientific studies have indicated that 1. The interaction of iron-rich minerals like olivine and dolomite with hot, subsurface water can produce natural hydrogen, and 2. The presence of magnetite acts like a catalyst for the reaction. However, in a recent paper entitled Reassessing the Role of Magnetite During Natural Hydrogen Generation, dated 2023, in the journal Frontiers in Earth Science by Hugo Gaiman et al., it was shown that the magnetite was more than just a catalyst in the reaction, but was actually the primary source of the hydrogen. Quoting from his article, for the purpose of experiments, gold capsules filled with magnetite powder and water were run at 80 and 200 degrees centigrade. After experimental alteration, high amounts of hydrogen were quantified. He also states that concerning hydrogen exploration, this work provides evidence that natural hydrogen can be generated at near ambient temperature. In the summary of the paper, he states, as for the future of native hydrogen exploration, these results demonstrate that magnetite lithology should be targeted while exploring natural hydrogen resources. The next slide shows quantitatively how magnetite supersedes other iron-rich materials in the generation of hydrogen. Based upon the experimental laboratory data taken from the aforementioned paper, the following question is posed. In the presence hot water, which is the best hydrogen generator, an iron-rich granite, olivine or magnetite? In this bar graph of material type versus hydrogen production, the lower temperature magnetite sample significantly outperforms both the iron-rich granite and the olivine in terms of hydrogen production. Based upon the experimental data just shown, we can consider magnetite as the primary source of geologic hydrogen. Question: can nanomagnetite be formed in the porosity space of an iron-rich dolomite like anchorite? The answer is yes, according to laboratory data and AI. According to the AI overview, magnetite can be formed in the pore space of iron-bearing dolomites. This process is known as diagenetic magnetite formation, meaning it occurs after the initial deposition of the sediment and during the burial and alteration of the rock. The SEM photograph in the slide is taken from a paper entitled Formation of Magnetite Nanoparticles by Thermal Decomposition of Iron-Bearing Carbonates by Alicia Cohn. It clearly shows a cluster of nanomagnetite particles on the surface of anchorite, which is an iron-rich dolomite. This answers the question of where the nanomagnetite came from that was observed while swabbing a porous anchorite zone in the Wildcat well shown earlier. Assuming the nanomagnetite generated in-place hydrogen, and no gas was observed during swabbing, the produced hydrogen must have moved up dip in the dolomite formation. This is the major point of exploration concept number 1. Returning to the geologic cross-section shown earlier, magnetite clusters have been added to the iron-rich dolomite. Hydrogen generation produced by the magnetite in the pore water has created an updip, unimpeded hydrogen pipeline which moves the hydrogen updip into the reservoir trap. The second, novel exploration concept deals with the formation of the low-angle recumbent fold trap formed by crustal uplift and ductile shearing. It is this type of deformation that can create the impervious granite caprock for the reservoir. Exploration concept number 2 deals with forming a shallow structural trap for the hydrogen gas produced by exploration concept number 1. Based on crustal uplift of pre-existing wrench folds which deform by ductile shearing, a low angle, recumbent fold is created on the unexplored backside of buried mountains. The recumbent fold can structurally trap upward migrating hydrogen within an iron-rich dolomitic reservoir rock which is sealed by a thin, impervious granite caprock. Let me explain. In this slide are two models representing the generalized, structural geology of a buried mountain created by a low-angle thrust in the granitic basement. The bottom model represents the traditional structural model indicating a deep frontal basin with stacked, faulted, and steeply dipping folds on the front side. Significant oil and gas fields are encountered on this side of the buried mountain. massive amounts of geophysical data are collected on the frontside in an attempt to image the hydrocarbon traps. Traditionally, the shallower backside is considered less interesting from an exploration standpoint, with little or no geophysical data due to low-angle, monoclinal structural dip. A novel structural model based on ductile shearing of the subsurface during uplift is shown on top. The model predicts a similar mountain front structural configuration with less emphasis on faulting and more on folding. However, the novel, structural model predicts low-angle, recumbent folding on the shallow backside of the buried mountain. The folding is capable of trapping hydrogen underneath impermeable granite. The almost flat-lying, recumbent fold creates a pancake-shaped hydrogen reservoir that is more or less featureless on conventional geophysical data. This slide illustrates how to create a buried mountain by crustal uplift of pre-existing surface folds assuming a ductile shearing rheology during uplift. The ductile shearing deformation occurs in both the basement and sedimentary rocks. On the left, uniform surface folds are displayed with the shearing angle shown in blue and the uplift grid in red. Because the uplift preserves rock volume, some of the surface folds are rotated clockwise on the front side of the uplift to form folds that appear to look like high-angle frontal thrusts. On the back side of the uplift, the surface folds are rotated counterclockwise to form low-angle, recumbent folds. This slide shows how the smoking gun hydrogen prospect generally agrees with the novel structural model using ductile shearing deformation, the main difference being the Wichita unconformity that is present in the actual prospect. Again, the pancake-shaped hydrogen reservoir associated with low vertical relief doesn't stand out on geophysical data. This slide points out the lack of geophysical data on the backside of the Wichita uplift. The mountain front side of the uplift is densely covered with seismic data where the prolific hydrocarbon structures exhibit significant vertical closure, steep dip and stacked pays. On the backside of the uplift, where the sediments are gently dipping and the basement is shallow, flat-lying, recumbent folding can be disguised as bad data. As shown in this slide, seismic data covering the prospective area on the backside of the Wichita uplift is non-existent. If the prospect is hydrogen-rich, it should open up vast new exploration areas along the buried mountain. This mechanical modeling method shows how to form a slightly recumbent, near-surface, transpressional fold into a flat, low-lying recumbent fold using crustal uplift combined with ductile shearing. The final fold strongly resembles a large-scale, low-lying recumbent fold in Greenland. The upper limb of the fold has been eroded by an unconformity. The height of the fold in the photograph is estimated to be about 2,500 feet. Let's take a closer look at the structural dip closure on the underside of the flat-lying recumbent fold. A hypothetical gas-water contact in red has been added to the underside of the recumbent fold. Notice the underside of the model recumbent fold rises above the horizontal gas-water contact, thus signifying vertical structural closure. The presence of closure and overlying seal suggests the possibility of a trapped hydrogen reservoir. Based upon the recumbent fold model, the overall shape of the possible hydrogen reservoir is wing-shaped with a thick leading edge on the right which tapers gradually down to a trailing edge on the left. As will be shown in the third novel concept utilized in this prospect, the wing-shaped closure is significant in that it produces a characteristic gravity signature that can be used to verify the presence of a very low-density gas like hydrogen. The third novel exploration concept shows how gravity data can be used to locate hydrogen reservoirs within recumbent folds on the backside of buried mountains. The location of the Smoking Gun hydrogen prospect is highlighted on both a Bugaj gravity map and a recent 2025 map of hydrogen prospectivity in of the United States. If you look carefully, you see a correlation between buried mountains in pink with high hydrogen prospectivity in darker blue. This signals that the success of the Smoking Gun exploration concepts can be applied in many other locations in the United States. As shown earlier, the Smoking Gun hydrogen reservoir in blue is located within a basement-involved, low-angle, recumbent fold that has been eroded and capped with a thin, impervious granite caprock. For unbelievers, the occurrence of basement-involved, low-angle recumbent folding is shown in the photographs below. The wing-shaped reservoir with the leading edge on the right and the trailing edge on the left has been verified by the mechanical modeling just shown. Since the reservoir is relatively shallow and contains very low-density hydrogen, its presence can be verified with gravity data. Let me explain. The uplifted, high-density, granitic basement rocks of the buried Wichita Uplift are easily visualized using airborne gravimetry. The map on the left is a residual Bugaj gravity map which shows areas of thick, dense igneous rock in pink, signifying a buried mountain range running northwest to southeast. There is little color variation along the buried mountain range, indicating a uniform rock composition. On the right, a horizontal gradient map is calculated from the residual Bugaj gravity map on the left. The gradient data highlights small lateral changes in rock density. Notice the dramatic color change in the center of the ridge, signifying a significant change in rock density. Because the anomaly is located south of the steep mountain front defined by the interpreted Mountain View Fault, the anomaly lies on the backside of the Wichita Uplift and because of its triangular shape defines the hydrogen reservoir. The next slide shows a closer view of the anomaly. In this slide, the horizontal gradient anomaly which defines the low-lying, subgranite hydrogen reservoir is shown in an expanded view. The anomaly is triangular and unique in both shape and color variation. It is characteristic of a shallow, porous, triangular-shaped reservoir filled with very low-density hydrogen gas that was created by the structural uplift of a pre-existing wrench fold which has been deformed by ductile shearing. The triangular anomaly appears to be stretched out in the southwest direction, which is the direction of maximum structural dip. In this direction, the rocks have been stretched out and thinned by ductile shearing during uplift, which formed the almost flat recumbent fold. Also, in going from the northeast side of the triangle to the southwest vertices, the color gradient goes from sharper to duller. These observations are consistent with a folded, triangular reservoir which is wing-shaped in the northeast to southwest direction. The northeast being the leading edge and the southwest the trailing edge of the wing. The blue color, where the gradient is lowest, corresponds to the maximum thickness of the reservoir. On the right, the area of maximum thickness and calculated reservoir area are drawn. The concept of a stretched-out horizontal gradient anomaly shape due to a wing-shaped hydrogen reservoir is explained in this slide. On the left is the horizontal gradient gravity map across the Wichita Uplift showing cross-section AA' passing through the triangular-shaped gravity anomaly shown in the previous slides. The Smoking Gun prospect along cross-section AA' is shown on the right, with the hydrogen reservoir, in green, contained within the iron-rich dolomite, which serves both as a reservoir and source rock for the hydrogen. The upper limb of the recumbent fold has been removed by the Wichita unconformity, leaving a thin, very low permeability granite caprock to seal the reservoir. A gravity model of a shallow, wing-shaped, low-density gas reservoir encased in granite is displayed above the geologic section. The modeled gas reservoir looks like an airplane wing, with the smallest horizontal gradient value occurring at the thickest point in the reservoir near the leading edge of the wing shape. The trailing edge of the wing stretches out the color changes like we observe in the field data. As shown on the map, this novel geophysical interpretation pinpoints where to drill a test hole for maximum reservoir thickness. The calculation of estimated recoverable hydrogen reserves in the Smoking Gun prospect is based on the approximate shape of the subgranite closure, which is gained from gravity and structural geology modeling. The Smoking Gun subgranite reservoir shape on the left is approximated by the rectangular pyramid shape on the right. The shape is consistent with folding an asymmetrical, anticlinal wrench fold down dip to form a low-lying recumbent fold. Based upon the reservoir properties and gas composition shown in this slide, which assumes a gas that is 70% hydrogen and a reservoir rock that is 12% porous, the estimated recoverable white hydrogen gas volume is 64 BCF. This amount of hydrogen has an approximate value of $151 million, assuming a market price of $1 per kilogram of white hydrogen. This ends my presentation. Thank you for viewing it.